So this is my home page for where I work at CCT, the Center for Computation and Technology, also known as the Digital Media Center. My physical office is 2035 Digital Media Center. I don't know if I will go there at all this semester. I might. My background is from physics. I originally did simulations of rotating black holes. You can find my publications there if you're interested. This is my phone number in case you need it for some reason. This is my CCT email, which is the one I use most often and which I'm most likely to see. Okay. On this homepage, I have a link to what we call the official course homepage. There's also a link to this from Moodle. So this has an about, and it talks about the book that we're going to use, The Art of Multiprocessor Programming. You should get a copy. The book it's a very nice book in many ways, but one of the fun things about the book is many of the coding examples contain bugs and things that don't compile and so on. This could be a benefit because it keeps you on your toes more. You have to think. You can't just look at what they give you and trust it. And we'll be talking about various bugs and code errors as the course goes on. I have a syllabus, so look at how organized we are. I have a plan. Now this marks our class day as Fridays, which officially it is, and I will be having office hour at 10:30 on Fridays, as well as 10:30 on Thursdays. And the Zoom links for those are in Moodle. But in any event, this shows for each week what we're going to be covering from the book. The days that are marked as review, those are your days to ask questions. I will provide some questions of my own if you can't come up with any, but you really should be able to. We will also talk through an old midterm of some choice. The midterm exam, I don't know how I'm doing that yet. I'm thinking about a bunch of different things. This class is 100% online, but I could imagine us gathering outside in the quad and taking it there if that seems acceptable to people. I really don't want to go inside a building, but we can talk about it. I might just have to come up with another option. I still have a little time to figure that out. So you can see all the chapters we're going to cover, when the midterm is going to be, and when the final is going to be. I need to know from each of you if you have any particular problems, like if you get a grade lower than a B in this course, will you get kicked out of computer science? Or, will you lose your standing as a graduate school if you don't get a certain degree? Whatever kind of academic problem you might be facing, I would like to know what it is. In fact, maybe I'll make that an official question. What is the minimum grade you need to have to avoid something bad happening? I need to know this just so I can make sure to keep you on course. This is an elective course. I want you to be glad you took it. I don't want this to be a source of terror in your lives. Since there's only 2 of you listening, feel free to interrupt me at any point if you have a question. Chances are, if either of you have a question, somebody else will have that same question. Okay, so this is the about for the course, and there's this part in here that I have to read. I know it's stupid, but when I first started teaching, the first time I reported a student for cheating, the LSU came back to me and said, "Did you tell them that they couldn't?" And I said, "What?" I mean, what kind of a thing is that? But okay, so here it is. No cheating will be tolerated, so you can't. LSU Honor Code governs all work in the course. Unless indicated otherwise, all written work handed in must be done only by the individual whose name appears on the document. Regarding student cooperation on the homework assignments, you may discuss with other students the homework problems. However, what you submit must be your own solutions. Your instructor is authorized to give you help on all work. Help will not be given if it provides an unfair advantage, however. Any deviation from these guidelines will result in severe measures such as lowering your grade or failing the course and notifying the appropriate authorities on campus. I assume there's no questions about that. You've been told. One of the things that's required for this course is that you be able to program. You have to be able to write code and understand code. And if you can't, you're going to have a problem. Most of the examples in this course are Java, but we are language agnostic. You don't have to use Java. You can use C++ or some other language. Try not to stump me with some weird language, though. I really would appreciate that. The basic grading is 50% for assignments and quizzes. Class participation is 10%, the midterm is 20%, and the final exam is 20%. So all of these things are important. Any questions? All right, I think that covers the basic logistics of the course. If there are any further questions on that, I hope you will all let me know. Okay. This is not what I wanted. Let me stop share. This is what I want. Ta-da. Okay. So this is a graph of Moore's law. There's probably a million of these things online, and there are some that are even a little bit more up to date. It gives you an idea of the way computers have been progressing in power. On the bottom, you see the year, and on the left-hand side, you see a logarithmic scale for the calculations per second per $1,000 in this particular graph. There's a number of different ways you can slice this. You can get transistors per square inch and so on. But however you measure it, you're going to see a logarithmic curve going up like this. We've been stalling a little in recent years, however. This was a graph I compiled last year. I don't think I need to update it again this year. This is a graph of the top 500 machines. What you're seeing is three numbers. So the top number is the speed of the top machine. The medium value, the orange, is the average of the speed of the machines on the top 500 list, and the bottom line is the slowest machine on the top 500 list. So what are those strange terms on the left-hand side? Well, flops means floating point operations per second. Okay, mega, M is for mega, G is for giga, T is for tera, P is for peta, E is for exa. Okay, so you can see that we're getting close to the exaflop era, which is just mind-boggling, right? So we have meta is 10 to the 6th, giga is 10 to the 9th, tera is 10 to the 12th, peta is 10 to the 18th, and exa is 10 to the 21st power. These are machines that take up entire buildings. They have their own power supplies that can be in the megawatt range, their own special cooling, and so on. So here is a mythical beast from long ago, the Uniprocessor. You wrote your code and it executed one step at a time in serial. This is more like what you're going to see on any modern machine, the shared memory multiprocessor. The shared memory multiprocessor allows you to work on several operations in parallel, and that's what this course is about. So multi-cores are growing. Last year when I gave this course, I mean, every year I update these things. And last year, you know, we had the AMD Rome 2nd generation with 64 cores come out, and the iCore 9 with 8 cores, and the Ryzen 9 with 12 cores. This year we have Fujitsu's 48-core A64FX chip. This is interesting because this is not an x86 architecture. This is an open source architecture called ARM, which is becoming more of a standard, especially in Europe and Asia. But it's the same thing that runs on your cell phones and on Raspberry Pis, if you're familiar with those machines. Then there is this bizarre thing called a Cerebras wafer scale engine, which has 400,000 cores, so-called, but they're optimized for AI. I'm not 100% sure what AI optimized means. Usually it means 16-bit floating point, so barely capable of any precision at all. And there is a new supercomputer coming out that is based on the Cerebras. I forget its name. Multi-cores are growing. I couldn't help but put a link, but mention this. During the recent Hot Chips 32 keynote, Intel's Raja Koduri, if I said his name correctly, said that in the next 5 years, performance will increase by 1,000 times, which would be a pretty significant advance. It will get us very solidly into the exaflop range. He expects 50 times transistor density and 50 times power density. The transistor density is, you know, better gates, 3D stacking, and so on. And recently, NVIDIA announced they have a DGX system which they sell for about $200,000, which achieves 5 petaflops on AI applications. So I assume that means 5 petaflops of 16-bit floating point operations, which are only usable for AI. So for reference, if you're doing a coastal simulation or a black hole, you're going to need, for a coastal simulation, you would need at least 32 bits of precision. For a black hole collision, like the things that I've worked on in my career, you need 64 bits. So anyway, why do you care about all this parallelism? Well, when you double your program's path length, your software must somehow exploit twice as much concurrency. So, you know, your traditional scaling process would be probably long before you were born, that you would have a uniprocessor that would just get faster, and your code would run faster. And then the multi-core era came up with a different way. So instead of just making the clock run faster, you make your code, you do more code at the same, you do more calculations at the same time. And this is how you hope it looks, right? You want it to scale like this. Unfortunately, it's not so simple. Very often what you see is this, right? You have 8 times as many cores, but you only go 3 times faster. And why is that? Well, parallelization and synchronization require great care. By the way, parallelization is a very hard word to say. Most people say parallelization, which actually kind of means the opposite from parallelization. But anyway, so this is a course overview. What we're going to talk about is models and algorithms, things that are possible and impossible. And we're going to talk about different architectures and techniques. We don't necessarily want to make you experts. I don't think we're going to succeed in doing that, but there are some things that you're going to understand. So, for example, you will understand at the end of this course why modern multiprocessors have a compare and set instruction rather than some other atomic instruction. Sequential computation looks like this. You have an object, you change its state, you have a new object, you change its state, and so on. Parallel computation, you have threads where you have several objects in memory and you have different CPUs changing the objects and producing new objects. The problem, then there is asynchrony, which means calculations, each processor can work at its own speed. It doesn't have to match up with what the others are doing. And asynchrony is nice because it can handle certain unpredictable delays that can happen, like cache misses or page faults, or whatever other things can go wrong. So a cache miss, in case you aren't familiar with the term, computers have different levels of memory which they can access at different speeds. Generally, you have your main memory, then you have your third level cache, your second level cache, your first level cache, and at each level, the amount of memory gets smaller and the access gets faster. And the point is that the cache memory is so much faster than main memory. It's like the difference between reaching into your desk for a pencil and going out to the store and buying one, right? In order to access something. So the basic model that we're looking at is we have multiple threads. It says sometimes called processes. I should have changed. I should take that out of the slide. There's a single shared memory. Objects live in the memory, and unpredictable asynchronous delays can happen between memory updates. So we are going to focus on principles first, then practice. We're going to start with idealized models. We're going to look at simplistic problems. We're going to emphasize correctness over pragmatism. And correctness may be theoretical, but incorrectness has practical impact. If you can go fast but get the wrong answer, it's really of no help. So some general jargon, we have hardware, which has processors, and processors usually have cores. And cores are usually the thing that maps to a thread, a single worker. On the software side, you have threads, and multiple threads share the same memory, or you have processes, and processes don't share memory, but they do run on the same SMP. So here is a small parallel challenge. We're going to print the prime numbers from 1 to 10 to the 10th. And given 10 processor multiprocessor and 1 thread per processor, we're going to try to get a 10-fold speed up. So what do? Well, just being naive, you could split the work evenly. Each thread tests a range of 10 to the 9th numbers. And this is our pseudo Java code. So obviously Java doesn't support superscripts to do exponentiation. In fact, it doesn't have any built-in operator for exponentiation. And it generally doesn't have a thread ID class with a .get method on it. But let's not worry about those things. This is pseudocode, really. It's Java-like pseudocode. And so what we're going to do on the first line, on the first line, we're going to get the thread ID, and then we're going to do this little calculation to find out which of the numbers we're going to check for being prime. And each one is going to get its partition of 10 to the 9th numbers. We have some function that determines if the number is prime, and if it is, we're going to print it. So these threads are going to run in parallel and print over each other. So issues, you can probably think of a number of problems with this, but higher ranges have fewer primes, and larger numbers are harder to test, so the workloads are uneven. It's clear that the one with the first batch of 10 to the 9th is going to figure out the primes before the others. But even apart from that, it's hard to predict. If you have a program and you just divide things up evenly, it's hard to predict which one is going to finish first and if the workload will be even. So we reject this as a basic mechanism. I mean, sometimes it works. So we need some kind of dynamic load balancing. And how can we do this? Well, if you've gone to the bakery and you've taken a number, or a butcher, and taken a number and waited to be called on, that's kind of the model that we're working with here. So we have a counter class, and the idea is everybody gets this number, and while the number is less than 10 to the 10th, we get and increment the counter, and we check to see if the number is prime. And this is a thing that is going to happen when I talk through these slides over and over again. I'm going to talk through the code, and then I'm going to forget that I have these nice little highlights that go over each line of the code. So there's the counter. Oh, isn't that fascinating? It's only that one. Okay. I didn't remember how it stepped. All right. So here's a picture of how things look architecture-wise. we've got the code living on the different CPUs, and they all have their own caches, and then there's a bus, and then there's the shared main memory, and the shared counter lives on the shared memory side of things, the memory that's slow to access. Okay, and then back to our code example that is looking at the loop and the increment and get. Okay, so let's talk about the counter. Okay, the counter has a get and increment method. And that, as it's written, is okay for single thread, but not for concurrent threads. So what does it mean? So when I say value plus plus, you're thinking, well, this is going to add 1 to the value, and well, it's going to, and then return the old value, right? But as far as the underlying system is concerned, this is actually 3 steps. So we copy the value into cache, say we increment the value by 1, and then we return the original value. And then, you know, so the point is these are distinct steps. And if you map it out and allow for things to happen asynchronously, you could have one CPU read a value of 1, write a value of 2, read a value of 2, write a value of 3. But at the same time, you have a second CPU that read a 1, maybe before the first one, and then didn't get around to writing it until after the first one wrote 3. And so this get and increment, as we originally wrote it, could produce incorrect results if it was carried out at the same time. And this is called a race condition. And in the hierarchy of problems that you will have writing computer code in your life, the worst thing is a race condition. The race condition is the worst thing because, well, you're looking at it here, and if you've got these 2 things that are just reading and writing, you can reproduce this problem with a few tries on your laptop. But it's more likely, if you're writing some complex piece of code for research or industry, that if you have a race condition, you'll have a problem that occurs only 1 time in 100 when you run your code, or maybe 1 time in 1,000, or maybe your customer will see something happen and it will never happen again, and you will never be able to reproduce it, and you won't have any idea how it happened. The problem is the probabilities of different race conditions can be extraordinarily low, which makes them difficult to reproduce. There are some tools to help you deal with this kind of thing, and we'll talk about them later on in the course. But basically, if your code has race conditions, you have a nightmare. So the question is this problem inherent? If we could only glue reads and writes so that you don't have these overlaps. And so here's our challenge. We've got this code, and we want to make those 2 steps atomic, that is indivisible. We want it to be impossible for any processor to see something, to get in between those. And what we have is a read, modify, write instruction. So I told you that one of the things we're going to figure out in this course is why computers have a compare and set instruction. And this one, what we're looking at is this read, modify, write instruction we're looking at just needs to increment things by 1. And that's another instruction that you could put in the hardware, but really it's not as good as compare and set. And we'll talk about, as I say, we'll talk about why you need compare and set specifically. If you're writing Java code, there's keyword synchronized, and it doesn't look exactly like this because you have to supply the synchronized block with a variable, but this is pseudocode again. And what happens is you take these 2 lines and you say that we don't want anything to happen. We don't want anything to interrupt these 2 lines. Only one thread can do those 2 lines at once. And that's as I say, a synchronized block. And what we want to happen is mutual exclusion. We want this code to exclude all other threads from operating. So now we have a parable about this, about mutual exclusion with Alice and Bob, which are the 2 canonical figures from any computer science example because they have an A and a B, and they have both genders, they have 2 genders covered. So Alice has a pet, and Alice can let her pet into the pond, and Bob has a pet, and can let that into the pond, and the pets don't get along, so we can't have them in the pond at the same time. Okay, there are two formal properties in asynchronous computation, and these are important for you to think about. We have safety properties, which means nothing bad happens ever. And then we have liveness properties, which are something good happens eventually. So your computer can be safe if you turn it off. It will never produce a wrong answer if you turn it off. But that's not necessarily good enough, okay? So we want to formalize our problem. We have mutual exclusion. Both pets are never in the pond simultaneously, and this is a safety property. And we have no deadlock. If one wants in, it gets in. If both want in, one gets in. This is a liveness property. So we have a simple protocol. Just look at the pond. Gotcha. Trees could obscure the view, or you just miss that it got in. Or you look at the pond and then you go to you both look at the pond at the same time, and then both let their beasts out at the same time, and then you've lost. So, and that's kind of what the trees metaphor is. Threads can't see what other threads are doing. I mean, they can, some kind of explicit communication is needed. And message passing isn't what we want to use. The recipient might not be listening or even there at all. Communication needs to be persistent, like writing, not transient, like speaking. So we have a CAN protocol that looks something like this. Bob conveys a bit by pulling on the string and knocking over Alice's can. Can only be reused if Alice resets. Otherwise, Bob runs out of cans. The cans are on Alice's windowsill, and the strings lead to Bob's house, and Bob pulls the string and knocks it over. And so this, as I said, gotcha, can only be used if why is that out of order? Oh well. So the interpretation is we can't solve multiple exclusion for n threads with interrupts. So the sender sets a fixed bit in the receiver space, and the receiver resets the bit when ready. And this requires an unbounded number of interrupt bits. In particular, it would require n squared bits if you had n threads, right? Because each one would have to have a thread. Each one would have to have a bit in the other space. So an alternative is the flag protocol, where each has a bit in their own space and they control it. So Alice's protocol, sort of, is she raises her flag and lets her pet in. And Bob's protocol, sort of, is he raises his flag and lets his pet in. And here's Alice's protocol in more clarity. So she raises her flag, she waits until Bob's flag is down, and then she unleashes her pet. And then she lowers her flag when her pet returns. Okay, and Bob's protocol looks like this. And he raises his flag, he waits for Alice's flag to be down, and he unleashes his pets, then he lowers his flag when his pet returns. So I've got 3 of you online. Does anybody think this is unsafe? By the way, you may not know this, but one of the things in your controls on Zoom is a little button where you can do a thumbs up or a clapping of hands, in case that's something that you feel you want to do. Also, I can do polls. Let's just experiment with this. I'm going to do a poll. All right, I've gotten 1 response. Let's see if we can get 3 responses. 2 responses. Yes, we did it. End polling. Look at that. So the answer is, and here I can share results. Look at that. Okay, so the answer is it's safe. This is a safe protocol. This is going to work. Let me rephrase it. It's not going to work, but it's going to be safe in that nothing bad will happen. The pets will not get into the pond at the same time. It is not. It fails on liveness though. Okay, so Bob's protocol. Problem is, right, they can both raise their flags, and they can both raise their flags, and then neither one of them can ever let their pet in because their flags will just stay up forever, right? And so the pets won't get in. So while it is safe, it is not live. This is the equivalent of turning your computer off to keep something bad from happening. We have a deadlock. Nobody can proceed. So here is a second protocol for Bob that tries to do things differently. So this raises a flag, and then while Alice's flag is up, he lowers his flag and waits for Alice's flag to go down. And once Alice's flag goes back up, he raises his flag again, and then we go back to the while Alice's flag is up statement. And only then does he unleash his pet. Okay, so this protocol, how well does this one work? Okay, so in this case, what's happening is Bob is deferring to Alice. We're not doing the same thing for both threads in the code. But the flag principle is this: we raise the flag, we look at the other's flag, and decide what to do. If each raises and looks, then the last to look must see both flags up. And so the question is, can we prove this works? And we try to prove this by mutual exclusion. The proof of this mutual exclusion, we're going to assume both pets are in the pond, and we're going to try to derive a contradiction by reasoning backwards. So consider the last time Alice and Bob each looked before letting the pets in. And without loss of generality, you can say Alice was the last to look. So you have Alice's last look, but Alice had to raise her flag before her last look. And then Bob's last look, you want to be before Alice's last look. And then Bob last raised his flag. But Alice must have seen Bob's flag, so that's a contradiction. So this protocol is going to work. And then we want a proof of no deadlock. We want to say if only one pet wants in, it gets in. And deadlock requires both continually trying to get in. But if Bob sees Alice's flag, he gives her priority because he's a gentleman, I guess. And so that's not going to happen either. All right. Anybody have any questions?
Could you explain the difference again? I didn't hear you, between a safety problem and a liveliness problem?
Yes, that's Nicholas.
Yeah, yeah.
Okay, so Nicholas, I'm going to have to go to I'm going to have to make a little log, and I'm going to have to write in it that you asked a question, because I have to keep track of who asked questions so that I can give you a class participation grade.
Okay.
But so you have the joy of knowing that you have asked a question.
All right. I am joyful now.
What's that? Okay, so safety, so liveness or safety means nothing bad happened, right? So something bad happening would be if both pets got in the pond at the same time and they fought with each other. Liveness property means that things happen in a timely manner. Okay, so in this case, if both raised in the original protocol, if both raised their flags, then the pets are never in the pond at the same time, so the bad thing doesn't happen. But that's because nothing happens, right? Liveness doesn't work. Does that make sense?
Yeah, yeah.
Okay. All right. So the problem is with the protocol as we have it, in case you hadn't noticed, is it's unfair. It's unfair to Bob. Bob's pet might never get in, or Bob might get in less often. And it also uses weighting. So if Bob is eaten by his pet, or Alice is eaten by her pet, then the other one's pet would never get in. So mutual exclusion can't be solved by transient communication, but it can be solved by persistent things. It can be solved, or it can't be solved by interrupts. It can be solved by one shared variables that can be read or written. And generally speaking, we prefer a flag over a can. So the fable continues. Alice and Bob fall in love and marry. Then they fall out of love and divorce. And she gets the pets and he has to feed them. Okay. So this leads to a new coordination problem called producer-consumer. And producer-consumer is special. So the way this works is Bob puts his food in the pond. And then Alice releases her pets to feed. And the way this works is Alice and Bob can't meet. Each has a restraining order on the other. So he puts food in the pond and she releases the pets. And we have to avoid releasing the pets when there's no food. And we want to avoid putting food out if uneaten food remains. Okay? So these are our safety properties that we have. These are the things we want to avoid. The liveness properties is we want the pets to eat. So we need a mechanism to know, so that we know that, so that Bob can let Alice know when food has been put out, and Alice has to have a mechanism to let Bob know when to put out more food. Now, we told you that the CAN protocol is no good, but it turns out that in this case it is. And part of the reason that it is producer-consumer is inherently a two-thread problem. We have one thread that's producing and one thread that's consuming, and so we don't have that n-squared problem that we had before. So the idea is, Bob puts the food in the pond, Bob knocks the can over. The pets can feed, Alice resets the can when the pets are fed. And what's nice about this, not only can we use the CAN protocol, but we really don't need to use any kind of special synchronization mechanism at all. We can just use memory as it is. We don't need to use atomic instructions, and we don't need to use locks. Okay, so the pseudocode looks like this. Okay, while true, the can while the can is up, so while true is just going to be a forever loop, right? And then while the can is up, we wait, and then we release our pet. Alice recaptures her pet, and then she resets her can. Okay, and Bob's code is forever. He's going to, while the can is down, he's going to stock the pond with food, and then he's going to knock the can over. And the key that makes this work is Alice only ever turns the bit off, and Bob only ever turns it on, right? And they only do it when they already know it's in the other state. So we don't need, that's the reason we don't need special synchronization. And this is the producer-consumer problem. It's special because of this. Okay, and so we have mutual exclusion. The pets and Bob are never together in the pond. We have no starvation. If Bob is always willing to feed and the pets are always famished, then the pets eat infinitely often. And the pets are never in the pond unless there's food, and Bob never provides food if there is unconsumed food. Okay, so those are the three things we have. We have the safety, and we have the liveness, and a description of the problem. Okay, we could also solve the problem using flags. It's largely equivalent. And both solutions use waiting, while mumble. Okay, now waiting is problematic. In producer and consumer, it's inherent, right? But in general, in writing parallel code, waiting is problematic. If one participant is delayed, so is everyone else. And delays are common and unpredictable because you can read or write memory from cache, and you can have a cache miss, which means that that you have to go back to main memory, and that's going to take a long time. So at the moment, we're just pointing out that waiting is a problem. But our fable drags on. Bob and Alice still have issues. They need to communicate. They agree to use billboards. So this is the way it works. So we have Alice writes, "Wash the car." And after delivering that message, she wants to send another message, "Sell the lava lamps." And she writes the word "sell," and then Bob reads the message, "Sell the car." Okay, so this obviously won't work out. So we want to write a protocol such that the writer writes one letter at a time, and the reader reads one letter at a time, and the reader sees the old message or the new message and no mixed messages. And this is easy with mutual exclusion. We can just say, I take control of the billboard, I write. And I take control of the billboard and I read. But mutual exclusion requires waiting, and one waits for the other, and everyone executes sequentially. Remarkably, we can solve read-write without mutual exclusion. Why do we care? We want as much of the code as possible to execute concurrently. A large sequential part implies reduced performance. And Amdahl's law says this relationship is not linear. I didn't want to do that. Hold on. So I'm trying to figure out, I'm going to try to use polling again, because I think once we have a full-size class, that's going to make sense. But I see, this is how I do it. So bear with me here, because it takes just a minute for me to type this, but I need practice. I need practice at doing this, just so that we can, make use of this in the class. Okay, and now I can go to polls. And launch polling. All right, you have a poll. Basically, do you know what Amdahl's law is? Have you ever seen it before? And I'm missing the word law in the question, but whatever. One answer. All right. So one of you knows. Amdahl's law. So thank you for that. Amdahl's law says that we have the speed up of our code is our old execution time divided by our new execution time. So if our old execution time was 1 hour and our new execution time is half an hour, then we have a factor of 2 speed up. If our old execution time was 1 hour and our new execution time is 1 minute, we have a factor of 60 speed up. Okay, so it makes sense. And Amdahl's law looks like this in more mathematical terms, and it's actually quite simple. P represents our parallel fraction. So if our code is 80% parallel, P is 0.8. And 1 minus P is our sequential fraction. So the part that isn't parallel is sequential in this idealized simplistic way of looking at our code. And so if we have 80% parallel code, that means we have 20% sequential code. And the idea is we have n is the number of processors, and we can divide the parallel section by the number of processors. So if it's 80% parallel, then that 80% of the code can go twice as fast if I have 2 processors instead of 1. That's the basic idea. And so that's how this formula comes about. And so let's say I have 60%, 10 processors and 60% concurrency, which, that's pretty good, right? Most of my code is actually parallel then. How close do I come to 10-fold speed up? And the answer is I can only go 2.17 times faster. That's it. As fast as I can go on 10 processors if I have 60% of my code in parallel. And if I have 80%, then I can go 3.5 times faster, which is not impressive. And even if I have 90% of your code is parallel, you have to feel like that's an A for your code, right? 90%. And your speed up is going to only be about half the number of processors that you have. It's 5.26. And then if you have 99% concurrent, you can finally get close to 10-fold speedup. You can get up to 9.17. So making good use of our multiple processors or cores means finding ways to effectively parallelize our code and minimize the sequential parts and reduce the idle time in which threads wait. By the way, I want you to look at this and think about this, all right? 10 processors is a fair number of processors for a core, but typically, right, our newer machines have 48 on them. And to get 48, you need a much higher percentage of peak. I mean, a much higher percentage of concurrency than you need for 10 processors. And then you look at our modern supercomputers, which have billions of cores at the same time. And you have to think that almost everything has to be almost completely independent in order to get the use of the machine. So this is a very difficult problem, and there's a lot of thought that you have to put into these things. So the moral is making good use of our multiprocessors or cores means finding ways to effectively parallelize our code, which means we have to minimize sequential parts and reduce idle time in which threads wait. Waiting is bad. So this is what the course is about, the percent that is not easy to make concurrent, yet may have a large impact on overall speedup. And we're going to have a more serious look at mutual exclusion next week. Okay. So that takes us now that takes us to the end of the covering of chapter 1. In this lecture, we're going to actually cover 2 chapters. We're going to cover chapter 1 and chapter 8. And you're thinking, what the heck? 1 and 8. But really, my feeling is if you have any exposure at all to parallel programming, any exposure at all to locks and mutual exclusion, that's basically what chapter 8 is about. So I think it makes sense. It's part of the groundwork, in my opinion, although from another perspective, it isn't, right? So next week, we're going to learn a bit about how locks work. But at the moment, what I'd like to do is I'd like to switch gears, and I'd like to talk about how to use locks. So let me just pause at the moment and ask if there's any questions on chapter 1. Remember, for your class participation grade, everybody needs to ask a question once a week on the subject matter. And you have a whole other chapter to ask questions on that I'm going to cover, but you just have to make sure you ask one. So those of you who have not asked questions yet, be thinking about what you're going to say. It doesn't have to be an intelligent question, although those are nice. I just need to make sure that you ask one. All right, share screen. How do I know if I've got the right one? I believe I have the correct one. All right, so chapter 8. Why won't it advance? Okay. In this chapter, we're going to talk about monitors, conditions, reader-writer lock, reentrant lock, and semaphores. So monitors are a method of combining synchronization and data. An instance of a class that provides mutual exclusion to its methods. So the idea is, if you're doing an object-oriented programming, you want the object to manage all its own mutual exclusion, and you don't want to even know about it. That's what a monitor is for. So a monitor is composed of methods, locks, and conditions. It was invented by C.A.R. Hoare and Perbench Hansen in 1974. By the way, I saw Hoare speak at a conference, and he's brilliant, but I have never seen worse transparencies. I mean, worse slides. I've never. It's just mind-boggling. They were all completely blank with a single line that went from the left margin to the right margin in black text on a white background. That was every one of his slides. Any one of his slides was like that. Okay, monitors. So suppose we have two threads, a producer and a consumer, and suppose they share a FIFO queue and a lock to allow access to the queue. The producer code could look like this. Okay, so I'm going to just go out and say this is bad code. I mean, you're thinking, how could it be bad, right? I mean, it's only like 5 lines of code or 6 lines of code if you count the curly bracket as a line, right? It's almost nothing. And not only that, but it's manifestly correct, right? So I've got this mutex that I'm locking, right? And then I enqueue my stuff into my queue, and I have a finally block for the unlock. And the finally block means that, you know, even if some kind of exception gets thrown here, the unlock is still going to happen. So I won't leave the lock in a bad state. And you might be asking, how could there be anything wrong with this code? And what's actually wrong with it is kind of subtle. The problem is, it's not that it's incorrect. The problem is that every time you want to access that queue, you have to make sure that you use that same lock. And that means that you have to, while these are only 6 lines of code, you have to replicate them everywhere. And if at some later time you want to use a different lock, you have to change every one of those places, right? And you always have to think through what you're doing with your locks. And this is why we want to move the lock inside the queue class itself, okay? So when the queue is full and the Enqueue method cannot execute, it has to wait. And when there are multiple threads, each must keep track of the data and lock objects and maintain the same locking mechanism in order for the application to be correct. The thread doesn't have to have access to the internal state of the queue. And providing the queue with its own class and internal lock, each method first acquires it and releases it, and the Enqueue and DQ methods will decide whether to block the producer or the consumer. So a monitor, as I said before, is basically a class representing a shared resource comprised of locks, conditions, methods that acquire the locks and release the locks, and this is mutual exclusion. And this allows mutual exclusion on the class. It also has its own data. So the advantages of using monitors are that synchronization code is written internally to the class. The users hopefully don't need to know about it. It works for multiple threads accessing the same shared object. And with the use of conditions, a thread may relinquish the lock if some property does not hold. Okay, so when a thread fails to acquire a lock, it can act in one of 2 ways. It can busy wait, or it can, you know, which is preferred if you have short delays, but it's otherwise a waste of CPU time and can create extra heat and other problems. Or it can block. It can withdraw from trying to acquire the lock and letting other threads try. And this is preferred when the delays are long and the overhead of a call to the OS or other threads is involved. The possible combination is the thread spins for a short period and then blocks for a certain period if it doesn't succeed. Let's see, what time is it and how are we doing? Just want to check. We're at 11:30, so we're at about the hour mark. Anybody feeling mental fatigue from listening to me talk for an hour? We could take, why don't we just take 5 minutes and you get yourself some water maybe, and then we'll come back and, you know, bathroom break and water break or whatever, and then we can come back and we can plow ahead, okay? What do you say? Good? All right, take 5.
Oh, sorry, I didn't mean to.
Okay, go ahead. Ask your question.
Oh yeah, I'm just asking if I'm understanding what a monitor is correctly. It's basically just like a third party to the threads that are trying to access the resources that keeps track of like the locks on the resources.
No.
Correct.
So the idea behind a monitor is we have an object that's keeping track of its own concurrency with its own locks and its own condition variable.
Okay.
It's not a third party in any sense. It's of the two parties, right? It's the object, not the user of the object, that's keeping track of the concurrency.
Oh, okay, okay. Gotcha.
So if you have an object and your object contains locks and condition variables which it uses, you have a monitor.
Gotcha. Okay.
I've marked your name down on participation. Is everybody back? Nicholas, Alexander, are you there?
Yeah, I'm here.
Alexander, are you there?
He said yeah in the chat.
Okay. He doesn't want to. All right. I'm glad you. So the chat isn't generally going to be as useful for me. Let's see if I can pull it up. Problem is, I only have so much space. There's the chat. I've got 3 messages in the chat. Oh. All right. Look at that. The chat has been getting used. All right. Don't count on me seeing the chat, please. All right, so conditions. The motivation here is when a thread is acquiring a lock of an object, it is waiting for something to happen before it can proceed. It needs to release the lock in order to let other threads access the object so that that condition can come about. I'm not happy with the way those words came out of my mouth. But let's plow ahead and it'll become clear, I hope. So a condition is a class associated with a lock, and it's created using the new condition method of the lock interface. And when a condition occurs, a thread that is waiting may be awakened to try and access the monitor. And it's part of a well-defined monitor. So the void await method is called when a thread wants to wait for a certain property to hold. And the signal method is called when a thread wants to wake one or more threads up that are waiting on a condition. And before returning from await, the thread must reacquire the lock associated with this condition. And signal all is the same as signal, only it signals all waiting threads. When signal all is called, the threads waiting are either, whether signal is called or signal all is called. When signal is called, one thread is awakened, and signal all threads are awakened. And this does not necessarily mean that the property now holds. When the thread wakes up, the thing it's waiting for may still not have happened. So you have to check. The approach we're going to see is implemented in Java, and it's called non-blocking condition variables of signal and continue, and it doesn't guarantee the condition waited for will be true on wake up. The original monitor proposed by Hoare and Hansen used blocking condition variables, which did guarantee it. Okay, so condition variables, conditions example, we have a locked queue. We have one lock object, and we have 2 condition objects, a not full and a not empty. And the way it's going to work, when I show you the code, I'm hoping this will all make sense in case you don't know what conditions already are. So first we have the constructor. So we're going to create the lock. And well, this isn't technically a constructor. This is initialization. We're initializing the lock variable with a new lock. And then from that lock variable, we're getting 2 conditions. And then we have, inside our queue, we have an array of items with a tail, a head, and a count. Okay, and this is the way this looks. So if we look at the Enqueue method, when we're putting stuff into the queue, we're going to say while count equal items, not full await. So the idea is I can't put anything in the queue if the queue is full. So I say while the queue is full, I'm awaiting for the not full condition. Does that make sense? Let me rephrase it. I like to always put it as a negative. Does it not make sense? And then you can just scream at me. Okay, so while the queue is full, we wait for it to be not full. And after we put something into the queue, we signal that it is not empty, because it could be, right, that the queue was empty when we put our object in there, we put our data in there, and now that we put it in there, it's full again. So we want to signal not empty. Oops, did not mean to do that. Okay. On the other hand, when we want to dequeue, we want to do the opposite thing. We want to say while the queue is empty, we wait for it to not be empty. And as soon as it isn't, and as soon as we've done that, we dequeue our first element from the queue, and then we signal that it is not full anymore, which means an Enqueue method can proceed. Okay, and as before, we put our unlocks inside finally clauses. Doggone it. We put our unlocks inside finally clauses so that the unlock always happens, regardless of whether any exceptions are thrown. Make sense? Does it not make sense? Okay. Again, interrupt me at any time. There's only 3 of you. So now I want to describe something called a lost wake-up problem. That is, a thread might continue waiting even though the property it is waiting for has become true. And the scenario is that instead of calling the not empty signal whenever there's a dequeue, not empty signal is called only when we're moving from an empty state, say from, when there's one item in the queue. And so this is obviously an attempt by somebody to optimize this queue, and the optimization is going to go wrong. Okay, but it kind of makes sense, right? We don't want to signal not empty when we go from 2 items to 3 items, because that signal's already been given, right? And this is something that happens when we have multiple producers and or consumers. So the lost wake-up problem is like this. A and B try to dequeue an empty queue and wait on the non-empty condition. C enqueues and signals not empty, waking A. But before anything else happens, D enqueues. Okay. And this doesn't signal because there's already something in the queue. Now A dequeues and B does not, because only one signal was called, not 2, and there are 2 threads waiting. And so B suffers a lost wake-up. It's sitting there waiting, even though there's something in the queue. And then we have deadlock. Well, maybe not deadlock, but we have lots of waiting. So there are several rules of thumb to avoid lost wake-up. First, there's understanding the code. And this is hard, right? Because if you just looked at that code, you might not realize there was anything wrong. It looks like a sensible optimization. If you're going from 0 to 1, you send the signal, otherwise you don't. And you might, and the lost wake-up might not have occurred to you. It's sort of a deep understanding of the code. So something that you can do instead of doing a signal, you could do a signal all, and that would remove the problem, right? If instead of signaling one thread to wake up, we signaled them all to wake up, it would be fine. The third thing is you can wait with a timeout. So the await method has the option for you to provide some number of seconds, and when that number of seconds expires, it will automatically wake up and check to see the condition, whether the condition is achieved. And my feeling is that if you're doing this, if you're waiting with a timeout, you're probably so lost and desperate to get your code working, and you have no idea what's going on, that you just don't know what to do, and it's probably not going to help. It always feels kind of hacky to me to use the timeout. I'm sure there's a use case where it actually makes sense, but in my own experience, I've only ever used this when I was desperate and couldn't figure out what was wrong. So signaling all tends to be the more safe thing to do. So unless you have a reason not to, I would recommend using it. Java provides support for monitors by using synchronized methods and also built-in methods, wait, notify, and notify all, similar to await, signal, and signal all. So the point is you have the synchronized block with a keyword that used to do things, and you can also do things in a way that uses classes, and the names are different. There's just two different mechanisms in Java. One other thing I want to point out about condition variables, let me go back. Okay, whenever you call await with a condition variable, it's inside a loop. If you write code and you have an await method and it's not inside a loop, you probably don't know, you probably don't have any idea what you're doing. Because the point of the await method is you're looking for some condition to be true, and you have to check to see if that condition is true before you proceed. Otherwise, and if it's not, you need to go back to waiting. So just one thing to remember about await methods is they have to be inside loops, generally speaking. Again, there might be a use case for not doing that, but I really don't know what it is. Okay. Reader-writer locks. Okay, so one of the problems, one of the things that people have told me in reviews in the past is that I speak too quickly. And I make all kinds of pauses for questions and nobody asks any. So I think it's as much a fault of my audience as me. But the nice thing is, with the format of the course this year, is that you can replay everything I say. And you can go back and listen to it again, and hopefully, if it didn't make sense the first time, it will make sense the third time. Okay, so what we want to do now is we want to describe another kind of situation, readers-writers locks. So readers are just that. They're going to look at the data, and they're not going to modify it. And writers want to modify the data. And it's clear that I can have any number of readers looking at the data at the same time without anything bad happening. The only problem is if I have two threads trying to write the data or one thread trying to read it while another thread tries to write it. Okay, so if I have lots of readers and very few writers, then having a readers-writers lock is a good optimization. So I have two kinds of locks, one for readers and one for writers. And yeah, and as I said, if you have more reader calls than writer calls, this is good. So we have an interface that looks like this. We have a read-write lock, and it can return a read lock and an associated write lock. And the two safety properties are a thread can only acquire the write lock if there are no other threads holding the read or write lock. And a thread can only acquire the read lock if there are no threads holding the write lock. Okay, so those are our two safety properties. And thus we can have multiple readers and we can have a single writer. So here is our simple read-write lock class. It contains a Boolean variable indicating whether there is a thread holding the write lock. And only when writer equals false can a thread acquire the read lock. And this contains a counter, the readers, indicating how many threads hold the read lock. And only when writer is false and readers equal 0 can a thread acquire the write lock. And so the lock and unlock methods are accessed through the objects of the inner class, read lock and write clock. Write lock, not clock. And it contains one condition for both reads and writes. So here is how the code looks. We've got our condition variable, our read lock and our write lock. And we instantiate everything. And then we have our methods to get those. When we get those methods, we just return the inner objects. And here's how the read lock works on the left. So you can see my pointer, right? You do a thumbs up. Yes, good. So when you want to lock, first you lock the reentrant lock we have inside our class, and then we say while writer we do a condition await. And then we increment our readers. So to increment the read lock, we make sure that the writer flag is false, and then we just increment the readers. and we want to unlock it, we just decrement the readers. And if the readers is equal to 0, we signal all. Hopefully that makes sense. It's pretty straightforward. Now the write lock class is going to do two things in its condition. It's going to check that the readers is 0 and that the writer is false. Okay, and it's going to wait until both of those are true. And then once they are, it's going to set writer equal to true. Doggone it. The unlock is simply going to set the writer to false and call signal all. Yes, question.
All right, could you go back to the read lock class really quick? I'm just still trying to wrap my head around the oh yeah, the conditions for when readers are allowed to read. Okay.
Right. So it's
only while there's
it just wants writer to be false. That's it.
Okay. Okay. Got it.
All right. And so the read and write lock methods synchronize on the same lock and condition variable of the simple read write lock class. And the advantage is it's always correct and it allows mutual exclusion. It's simple. Disadvantage: fairness does not hold. You might not have realized this, but if you think about it, you can see that it's true. If you have many readers and few writers, the writers could starve. They could just sit there waiting forever for readers to be done. There could be, 2 readers could start up, 1 reader could leave, 3 could come in, 2 could leave, 4 could come in, and they might never relinquish the lock for writing. So how do we solve that? We have to modify our code. We want a fair readers writers lock. And we want to ensure that once a writer has requested the write lock, no more readers can acquire it. So the current readers will finish, and then the writer will be able to acquire the write lock. And so here is a possible implementation. The readers counter field is replaced by 2, read acquires and read releases. And those keep track of the number of readers that have acquired the lock and the numbers that have released it. The writer field acts as a lock. And so the writer is set to true when they're requesting the write lock, even when there are current readers active. Okay, so the writer equal true now means there's a writer requesting the lock, or possibly a writer that has the lock. You can't really tell. Readers who see writer equal true can't acquire a read lock. And the conclusion is that when a thread calls for a write lock, it has priority over subsequent read lock calls. Writers are informed that there are no more readers when a reader releasing the read lock identifies that read acquires equals read releases. Okay, so here's how this code would look. So here is our FIFO read write lock, and what we have is in the constructor we set the read requires and read releases to 0, and we have the writer set to false, and we initialize our locks. The read lock now looks like this. We get our main lock, and we say while the writer lock is false, we await, and then we do read acquires, and then when we unlock, we do read releases. And then we say if read acquires equals read releases, then we signal all. Okay, so that says once this is true, there are no more threads holding the read lock. There might be many waiting for it though. The write lock, on the other hand, is going to start with waiting for the writer flag to be false. So that means there are no other writers either requesting or holding the lock. So it's going to start with writer equal false, right? That's what this loop does. And then once that's the case, it's going to set the writer flag to true. And then it's going to wait for the read acquires to equal the read releases. Okay, so basically you're awaiting the opposite of whatever the condition is inside the while loop. So it's waiting for these two things to be equal before it proceeds. And once you get past this, you now have the lock, right? So first you wait for the writer flag to be free, you set it, then you wait for reads to acquires to equal releases, and then you've got it. And when you unlock, all you have to do is set the writer flag to false. Does anybody have a problem with that? Okay, so this is how you make the read-write lock class fair, right? So if a writer comes on the scene and wants to write something, then no further read locks can be obtained until that writer succeeds. A reentrant lock. So up until now, we've just been invoking this reentrant lock without comment. But a lock is reentrant if the same thread can acquire it multiple times. And this is useful when a thread acquires a lock and then calls for a nested method that locks it again. So in some sense, this allows you to be a little sloppier with your code, right? You don't have to keep track of whether you've locked the object, right? Because with a regular lock, if you call lock and then you call lock again, you've created a deadlock with yourself, right? With a reentrant lock, the same thread can call the same lock multiple times without issue. So the locks package provides a reentrant lock, but here we're going to show you how to create one. So the idea is you have a thread calling the write lock for the second time. A normal lock will deadlock itself, but we want it not to. So let's just go ahead. We're going to use a thread ID capability to do this. So we're going to count the number of times the owner of the thread has locked the lock, and then we're going to decrement it when we unlock. And when the counter is 0, we can wake other threads up. So here's how it looks. So we have a lock, we have a condition, we have an owner of the lock, and we have a hold count. And the idea is when we call the lock, we fill in this me field with the current thread ID. Then we lock the lock, and if the owner is me, then we increment the hold count. This is a reentrant call. I'm locking for the second time, in other words. And so all I do is increment the hold count and I return. On the other hand, if the owner is not me, then I'm going to wait for the hold count to be 0, and then I'm going to set the hold count, the owner to me, and the hold count to 1. All right. Question. What's wrong with this code? It's terrible code. It's utterly fatal flaw. If you deployed this, you would almost instantly have a bug report. This is where I test to see if any of you are awake. So let's look at the lines of code.
Does it have to do with
I can't hear you. Speak up.
does it have to do with owner?
Can you be more specific?
I'm seeing how I'm trying to see it. I mean, it says it's an instance variable, it should start with 0 and it is instantiate. I'm trying to see how it wouldn't be owner, like when that would ever happen.
So the unlock method isn't shown here. When you unlock it, you're going to have to change the owner. Let me just go ahead to that. So here's the unlock method. In the unlock method, we lock our lock. We check that the hold count. If the hold count is 0 and the owner is not me, then we throw an exception because that shouldn't happen. Then we're gonna decrement the hold count, and if the hold count is 0, we're going to signal all. Right, so we can set the owner whenever the hold count is 0, right?
Okay. Yeah.
So that's not the problem. But let's compare this one, right? So we lock, we check for illegal state, we decrement, we possibly signal, and then we unlock, okay? Now in this one, what we do is we get our thread ID, we lock, we check the owner, we check the hold count, we set the owner, we set the hold count. This is why programming is hard.
Wait, why are you incrementing the hold count if you are the owner?
that's the whole point. The idea is every time the idea of a reentrant lock, if I'm the owner and I'm asking for the same lock multiple times, I don't want it to deadlock. So
Right.
what I'm doing
okay.
is I'm incrementing that hold count to say how many times I'm holding that lock.
I see.
And I have to unlock it as many times as I lock it. And then so long as I do that, everything should be fine. Okay, so I'm actually trying to give you a clue when I do this. I pop forward to this one, the unlock. So I lock the lock, I check for illegal state, I decrement the hold count, I check the hold count is 0 before I signal, and I unlock. Now let's go back and look at the lock method again. I get my thread ID, I lock the lock, I check the owner. If it's me, I increment the hold count. If the I wait for the hold count to be 0, I set the owner and the hold count. There's something I'm not doing. There's
Are you
something
not
that I'm doing. I'm not unlocking. It's kind of obvious, isn't it? I mean, now that I say it anyway. All right. Now, there's actually a problem with this one, too. I haven't thought, a potential problem, I should say. And I haven't really thought through whether it's a real problem, but it raises a concern in my mind. And rather than trying to make you guys figure it out, I'll just tell you. It's doing a signal instead of a signal all. So there's a potential for a lost wake up here. I have to think through if for some reason it doesn't happen. But there's a potential for a lost wake up there. I would put a signal all. All right, so this kind of problem, right? These slides don't come directly from the book, but these are the kinds of problems you see in the code in the book all the time. So what I encourage you to do, anytime you see code in the book, I want you to copy it into a file and compile it and figure out a way to test it. And more often than not, you'll find things that don't compile or don't work, and you have to figure out your ways around them. And that will help you. There was a study done where they had a lecture given where the lecture notes were all perfect, and there were no errors in them. And they had another way that the class was taught where there were errors in almost every slide. And it turned out that students learned better if there were errors in all the slides, because that caused them to more actively engage their brains in what they were hearing rather than just trusting everything. Okay. So just trusting everything I say or everything in the book is not going to help you as much as doubting will. So I encourage you to doubt. You should also doubt your own logic as well. I mean, this is one of the key things. There was Rene Descartes said, "I doubt, therefore I am." He was trying to come up with a philosophy that no one could argue with, right? And he said, "Well, what am I left with if I doubt everything?" And he decided that what he could not doubt was that there was someone doubting. Anyway, but what I'm encouraging you to do is doubt everything, okay? Check everything. Okay, semaphores. So far, we've seen mutual exclusion locks where only one thread can access a critical section at the same time. A semaphore is a lock with a capacity, an upper bound on the number of threads that can hold it simultaneously. So if we have a critical section and we want 2 threads to have it at the same time instead of 1, or 3 threads, or just some number that isn't 1, and we want to implement this. We're going to use a counter to count the number of threads currently holding the lock, and we're going to increment when one acquires and decrement when one releases. And so we have 2 methods, acquire and release. And the code is going to look like this. we're going to have a semaphore with a capacity C, which we're going to set with a constructor. So that's going to be the number of threads that can hold this semaphore at once, whether it's 2 or 3 or whatever. And then we have an acquire method. And we're going to say, while we're not at capacity, wait, and then increment our state, okay? And that's our acquire method. And our release method is we decrement our state and then we signal all. So this is like the safest way we could make this work. Okay, so monitors allow control of locks and conditions from within a shared object. Conditions associated with locks allow threads to wait and release the lock until some property holds. Readers and writers locks manage access to a shared object when both are reading and writing. And reentrant locks allow for a thread to acquire a lock that is already holding, and semaphores allow multiple threads to access the critical section. I'm going to add something else here that I somehow, in my head, I thought was in these slides, but it isn't, and it's a very important point. It's something about locks. And if you've used locks at all in your coding, you've encountered this issue. But the problem is locks are not composable. What does that mean? It means that if I look at some section of code that uses locks, I don't necessarily know how it's going to behave unless I know what the whole program is doing. And the reason is that let's consider the following situation. If I have 2 locks, A and B, and threads 1 and 2, and thread 1 acquires lock A, and thread 2 acquires lock B. Okay, everything is fine so far. But now, thread 1 wants to also acquire lock B, and thread 2 wants to also acquire lock A. We have a deadlock, right? Because each thread is holding on to one of the locks and is trying to get the other one. And the problem is, whenever you go to acquire a lock, you don't know what locks your current thread already holds. And so you don't know if what you're doing is going to be a potential deadlock unless you know everything about what's going on. Now, the way that you typically avoid this problem is that you try not to hold on, you try not to have any possibility of acquiring a lock inside your critical section. You want that code, whatever that code is, you want it to not acquire a lock. And then you want, when you do lock your locks, you want to lock them in some canonical order, so that if you want both lock A and B, you always get lock A first, and you always get lock B second. And if you can follow those rules, you won't deadlock. But the point is, you have to know everything about the code in the critical section. You have to know everything about any callouts it's going to do. You have to know everything that's going to happen in order to know that you're safe from deadlock. And composable means you can just look at things in isolation. I can just look at my critical section and I can know I'm safe, right? And that's something that locks don't allow you to do. And as I say, in part that's because you don't know what lock you already hold. So that's an inherent problem with locks, but it's the state of the art nonetheless. Are there any questions about that? Okay, so I have shown you, so most of what we've done today has been about terminology, right? So let's see if we can just review what we've learned there. We've got safety and liveness properties. We've talked about we've talked about fairness as well in the discussion of liveness. We have talked about Amdahl's law and the issues of parallelism and the perils of waiting. And we've discussed one of the most basic mechanisms for parallel control, which is locks. And we've talked about how to package them together with condition variables inside a monitor. And then we've discussed several implementations of monitors. this is all well and good, but what I think we need to round out this discussion is actual code. And I will post this code to Moodle. By the way, one of the things I'd like to try to do with this course is have homework assignments come in through GitHub Classroom. So you should all get GitHub accounts if you don't have one already. GitHub, Git is an important professional tool that any of you are going to need in any kind of real-world coding job. And even if you didn't need it for that, it just makes your life so much better. So I think we're going to work through the pain of you trying to use it and me trying to teach it to you. Unfortunately, I have not been able to get GitHub Classroom set up through Moodle yet. I'm still fighting with ITS over that. So, but I will provide, you know, homework assignments probably tomorrow, because technically I'm not teaching today. Technically, I'm just recording a lecture. Okay, so the thing I'd like to show you, as I said, is actual code. So let's go to a window. And what I've got here is a set of Java and C and C++ codes. Here's another thing. If you're going to do coding, and you have a Windows machine, the thing that you probably want to do is you probably want to get the Windows subsystem for Linux. The Windows subsystem for Linux allows you to have a bash shell. So I'm running on a Windows machine. What you're looking at in this terminal here is a bash window inside the Windows subsystem for Linux. So this is Ubuntu running inside Windows. And I've got various codes in here. So I've got VI, by the way, is my editor. It's alias for VI improved. This is I use VI primarily because I learned how to use it in the 80s. If you can even imagine a time that far back. And it's got lots of obscure keystrokes, but I don't have to think about them because they're all just internalized. It's like driving a car. I don't think about what I'm doing. It just happens, comes out of my fingers. So here is a Java class that that implements a race condition of sorts. So what it's going to do is I'm going to create a thread with an inner class here. The thread has a run method. The run method is going to count up to 1,000 and increment this shared variable, the static variable I. And then after it does that, it's going to print out the result. Okay, and then the thread is just going to be started and allowed to run. So if I do that, I say javec job 0 .java, Java job 0. I get all kinds of crazy answers, right? Get something different every time because I have a race condition. This one is a little different, right? Because in addition to starting all these threads, I join them. So joining means waiting for it to finish. Now this one produces the same answer every time. However, the reason it produces at the same time, the same answer every time, is because inside this loop, right, this 1,000 loop, I am starting a thread and waiting for the thread to join. So I never have two threads running at the same time. So I'm not doing parallel code here. I'm just sort of meaninglessly starting a thread and waiting for that same thread to finish. What I need to do in order to do something meaningful is I have to have a loop where I start the threads and a loop where I join the threads. So let's look at job 2. At job 2, what do I do differently here? Okay, so here, instead of joining the threads, I set daemon. And if you set, so normally what's going to happen with Java is the thread will have, all the threads have to finish for the program to exit. But if I set daemon to true, then a daemon thread doesn't have to complete in order for the program to be done. And so when I run this one, they don't all finish. I should get a lower number of threads, a lower number of my random number. By the way, I don't know how many of you are familiar with the Linux command line. We can possibly have some extra time to talk about that if that is confusing to anyone. If it is, definitely come to my office hours and we will talk through some of the issues with the Linux command line. But this is another thing that I think is going to be valuable for you to learn. In any event, okay, so here's Java 5, and in Java 5, I'm doing the thing that I described before. So first I create an array of threads, 100 of them, okay? And then for each thread, I'm going to instantiate that thread and store it in the array. And each of those threads is going to increment that shared variable by 1,000. And then I'm going to start that thread. And then I'm going to have a separate loop that's going to go through and join each of those threads. And as before, I'm going to get random numbers. But there's a little bit of a difference. Let's see if we can see it. I meant to do 0. Now watch what happens when this runs. If you watch very closely. There, did you see that? Sometimes you get multiple of these things happening on the same line. Not very often. With this one, it's far less likely that that will happen. Right? The point is that the print statements can overlap each other. Right? Like we had wash the car and stole the lava lamps. That kind of thing can happen with the print statement. Okay. This join thing kind of helps a little bit to keep things from overlapping.
What does the join method do exactly?
The join method waits for a thread to finish.
Okay. Okay, that's simple.
There you go. You got your participation grade. Congrats. Okay, so in this one, I'm using the synchronized block. The synchronized block requires an object, and now I'm synchronizing my axis to I every time I want to increment it. Now, this should work in the sense that one of these threads should always get the same number, but we don't know which of those threads is going to finish first, right? So, but the point is only one thread can increment this variable at a time, but that means that this is going to be much slower. That means that this code is going to be much slower than it's going to be much slower than if I just wrote a single-threaded code that just incremented I and didn't use threads at all. But nevertheless, the difference is this is a parallel code, which nevertheless forces itself to be synchronized for the only work it actually does. Okay, so here's job 7 in this increasing complexity, right? So we have our array of threads. We start them all inside one loop. We join them all inside another loop, and we synchronize. Oh, and what we've added at this one is we have an @finish, right? So we can see what the final variable value is. Before, we saw all kinds of random numbers because we didn't know which thread finished first. But this way, the @finish number is always reliable. It's always 1,000 times 1,000, right? Okay, so this one, so what I did before, right, is I had the number of threads and the number of increments per thread. I just had those embedded constants in my code. Generally speaking, embedding constants in your code is a bad idea, because that means when you want to go and change the code, you have to figure out all the places where you use that same constant, and you have to make sure you're consistent, okay? And you also have to figure out when you use that constant, what did you mean by that constant? I mean, I saw that there was 1,000 in the other one, and you could figure out that that's the increments per thread we were doing, but you didn't label it that, right? It wasn't documented as such. And so if I take these constants and I pull them out to the top of the code and I give them names, that means that if I want to change them, it's much easier. If I want to understand how to make the code do something slightly different, it's that much easier. And so that's what I'm going to do. And this code also introduces a new special thread called fin. And what fin is going to do is it's going to wait for this shared variable I to have a value that's equal to threads times increments per thread. So that's going to wait. That means it's going to wait for all the threads to finish, essentially. And it's going to use a condition variable to do that. There's a condition variable built into every Java class, and it's going to use the built-in one. And then once it's got that, once it exits from that synchronization block, it's going to print the @finish method. So what I'm going to do is I'm going to start that off. I'm going to start that thread off ahead of all the other threads. And then I'm going to launch all the other threads to do their synchronization. And this time I'm going to do all the increments inside the synchronized block. So at least I'm doing more work inside each block. And then at the end, I'm going to signal. So, and then I have my join loop, and then I'm going to wait, and then I'm going to join on the fin itself, okay, on the fin thread itself. Java is the Java compiler. I compile it. Java is the Java runtime. I run it, and I consistently get that number at the end. Java 9. Okay, so the difference is in Java 8, I always called the notify method, right? Every time I finished doing my increment, I called the notify method. In Java 9, I check to see that I'm done before I call notify. So I'm just trying to optimize the call to notify. It's really a very small change.
Oh, I have a question.
Yes.
What's the benefit of putting the that final line on in that method that's doing the wait?
So the point is, I shouldn't call that at finish. I shouldn't print the at finish until everything is done updating the shared variable, right? And there's just two ways of doing that. There isn't, you know, I can either wait for all the threads to be done, or I can have this other thread that waits for all the threads to be done. It really doesn't matter which way I do it. It's just showing you how to use the different mechanisms.
Okay, gotcha.
Okay, so I think, yeah, I think that's all the Java examples. Now I have the same thing done in C and C++. Let me stop this share for just a second. And then I will share my browser. And so I've got this side-by-side comparison in which I have the C and the C++ versions of things, in case you want to see how that's done in those languages. So here is the C version of creating all those threads, and here is the C++ version. So in C++ we have std thread. And we all know that std stands for standard. Okay, so in C you have to use the pthread library to get threads, and you have to create an object. You have to instantiate a pthread object. There's no constructor, so you then have to call pthread create on this, and you have to supply it with a task, which is a function that takes a void star argument and returns a void star. In C++, it's a little simpler. You can include thread. You instantiate a std thread with the increment method, okay? And that's all that you need to do. And these three codes, the Java, the C, and the C++, are all equivalent. And likewise, in C, you can use pthread join to join the method, or in C++, you can use a member function join, very similar to Java. The daemon thread in Java is detach in C, and it's detach in C++ as a member function. So if you look at pth3.c, the difference here is this code. There is no equivalent here, because the way pthreads work is they have these things called attributes, and you instantiate an attribute. Well, you create space for an attribute rather, and then you initialize that attribute, and then you can set the state of that to represent a pthread detached, and then when you go to create the thread, it creates it as a detached or daemon thread, so that the system doesn't need any kind of join. And that's a C only thing. And then 4 is also a C only thing, because it destroys the attribute as well. You actually I point out that this attribute, you can make a single instance of it and pass it to all the threads you create, because threads are going to just look at that data at startup, and they're not going to require it to remain valid. Okay, but you cannot, in principle, if you're using C, you should also release that space that you've allocated. You should also release that attribute when you're done with it. And then, let's see, 5, what did we introduce? We just had the different loops. So we have our join in another loop. In C++, we use a std vector to hold the threads. And so I have a std vector of std threads, and every time I instantiate a thread, I push it back onto the end of the vector. And then I go through the vector using an iterator like this, where auto is C++ filling in the type for you. And the type is going to be something like std vector, std thread, : iterator. And then the J is gonna behave similar to a pointer. So I have to use the arrow operator to call join. Then I have mutexes, and in C you need to allocate space for a mutex. You have to lock it, you have to unlock it, you have to initialize it. Okay, in C++, because it has constructors, you just instantiate it, and then you can use it with lock and unlock. Also, though, an alternative in C++ is you can have this lock guard. And what this will do is the instructor of a lock guard will lock the mutex, and the destructor will unlock it. So this is kind of like the equivalent of the try finally in Java. This is, except in C++, it uses the destructor mechanism. Conned broadcast is signal all. And let's see, condition variable, instead condition variable in here is CV. We have CV.notify all and CV.wait. Now, one of the interesting things about the way C++ implements the condition variable, right, is it implements it as a Boolean function. It's waiting for a condition to return true. It's really just sort of a vector of Boolean functions. And here we have a condition variable, cond init. We have, and we have cond wait and cond broadcast, we already said. Okay, and that takes you through the three different programmatic mechanisms for using the things that we've talked about in these two chapters. Are there any questions? Okay, typically you will find in this course, we do not use all the time allocated for lectures. It would just be too painful. This is going to be the end of your first lecture. And I think you will find that even though we did not make it to 1:30, your head really hurts sufficiently for it to be that for 3 hours, right? It hurts enough to have been 3 hours. So I invite you again, if anybody has any questions, speak up. There's only 3 of you here at the moment. Any questions about anything, about the course, about any of the things I've talked about?
You said we were going to get our first assignment tomorrow.
Yeah, I plan to work out exactly what I want you to do tomorrow. I may employ a Moodle quiz because I've never done that before and I'd like to try it, and I think it might be nice in this category, in this kind of course. But I'm going to try going forward to give you assignments that you turn in with GitHub Classroom.
Okay, well, does that work like normally, like how people upload things with GitHub or Git through like the terminal?
Yes. Yeah, it's so what you can do is you can do like a git commit and a git push, and then I will see your homework and I can grade it. And part of the purpose of doing that is just so that you can have familiarity with Git, which is, as I say, a tool that is virtually required for any kind of programming job, whether it's academia or business.
Okay, yeah, that's all I have. Thank you.
Yeah, if you don't have a GitHub account, get one. Any other questions? All right, That's the end of my talking for today. I hope that you enjoyed it. I hope you will keep me up to date on your academic progress and academic concerns and questions and ponderings and so on.